We are here in Boulder on East Campus at the Laboratory for Atmospheric and Space Physics. We're going to talk with Carl Himpsel today. Carl graduated from CU with a mechanical engineering degree, and he now works here at LASP as a mechanical engineer. Carl, thanks for joining us. We want to hear about your story of becoming an engineer. So maybe you can start off by telling us, when did you decide that you wanted to be an engineer?
It wasn't really a decision per se. There was no like singular moment that like, okay, I'm going to be an engineer. In retrospect, from sitting here to all the way back, like graduating high school and like, oh, I'm going to go into college, it looks like a very obvious career path for me. It's like, oh, you go in, you get an engineering degree, then you get your first job, and you kind of get to build some experience, and then all of a sudden you're building satellite parts. I just want to say it was not obvious at any point in the past that this is where I was going to end up or it was all going to work out like this. I could see maybe one step ahead and a general direction. So like coming out of high school, good at math and science, like, oh, you're good at math and science, you should go look at this. Also like working with my hands, building stuff, taking stuff apart.
Tinkering,
yeah. Initially, I wanted to do automotive engineering, or just work on cars. And so, yeah, went to CU, started as an open option, then moved on to mechanical, figuring that I could do anything I needed to in aerospace with mechanical. That it was a very general degree. After school, went to both Detroit and Audi in Ingolstadt, and I heard the same story in both places. You see that building over there, 3,000 engineers work there. And I decided that was not something, I did not want to hang out with 3,000 other engineers on a daily basis. That was just too big, too much. So I ended up not in the automotive industry, ended up at a small startup company, literally as the third person there, working out of a garage. Yeah, moved on from there to a slightly larger company and spent 2 years there as well, and then finally moved on to here.
And what do you do here at LASP?
So at LASP, I'm a mechanical engineer. Mostly I do the mechanical side of electrical systems. The electrical engineers will have their circuits and their schematics, and eventually that needs to get realized into a circuit board, a wiring harness, an electronics box, something that will hold together and withstand the rigors of the space environment and also getting launched on a rocket. I help them with that, getting it all lightweight into a very small volume, with the right amount of radiation shielding, making sure the heat that their electronics dissipate, and also that everything is plugged into the right spot and stays plugged in. So for example, one of the things that I've been working on is this guy. It's known as a rigid flex harness.
Okay.
So this is, I want to say, the electrical backbone of the GOES-R Exus instrument. This connects all the various detectors here on the smaller ends.
And what's the GOES-R? What's this going on?
This is the latest series of U.S. weather satellites. We have a very small instrument on there that looks at the sun and tells us how bright it is in the extreme ultraviolet and X-ray wavelengths. We use that to monitor what's known as space weather. When the sun lets out a large solar flare or something, we want to know about it here on Earth and take actions to make sure some of our satellite infrastructure doesn't get damaged.
So you built this, and it's going to go on a satellite that's going to be helping us detect abnormal weather.
First launch will be in early 2016. Very
neat. Can you tell us a little bit about what happens generally at LASP?
I work primarily in the engineering division, where the scientists will have a question. We need to take this data to help us answer this question. The engineers will come up with an instrument that will take that data and that will go out, get the right measurements at the right cadence, at the right accuracy. So the engineers take that from a general question and turn that into a real physical instrument that gets launched into space. Once it goes into space, that actually mission operators and sometimes even students that will control the satellite, keep everything pointed where it should, solar panels pointed at the sun, communication system pointed at Earth, science instruments pointing at whatever they want to look at, and uplink commands, downlink data, that sort of thing. They downlink that data, that goes back to the scientists, and hopefully they have their question answered, and most likely a whole host of new questions to ask.
So it sounds like you work on mechanical engineering issues at an aerospace facility. What type of problems do you solve here?
A lot of the problems that I solve here are are sort of specific to the aerospace industry, but they use a lot of general engineering principles, general science, physical principles that you would learn in any engineering discipline, mechanical, electrical, even civil or environmental. Will cover some of these basic things. It's your core classes. Thermal management is a big deal. Moving heat, from the sun, you're going to get very hot. Looking at space, you're going to get very cold, making sure that you're in your right operational temperature range. So a lot of stress analysis problems, that when you're going up on a rocket, things are shaking and it's really noisy, and your instruments might bend or break if they're not stiff enough or strong enough. Electrical problems, often working in conjunction with electrical engineers, is getting power where it needs to go, doing the things it needs to do, and then when it gets turned into heat, moving the heat away.
Right.
Fluid mechanics. As you go up on the rocket, you have to vent all your gas, the air from your spacecraft, so that it doesn't blow up like a balloon and literally blow up.
What people do you help?
Immediately, I help the scientists. I help them get the data they need at known accuracy, known cadence, known precisions. More generally, it's the general public as a whole is, in particular with the EXIS instrument, it's an operational instrument. So it's not just a science instrument. It goes out, it takes some readings, and we go back in the lab. It's used every day, all day, to monitor space weather, and people will use those predictions to make major decisions on things like flying satellites or flying airplanes, managing power grids, managing precision agriculture, and things like that.
How do you use what you learned in college at CU in your current role?
A lot of the basic principles come back, like I was saying, thermal management, electrical power, lots of stress analysis, a lot of material properties. Is material science is quite important. Is what, sometimes you'll want a material that's electrically conducting but thermally insulating, but yet also really light and strong. Sometimes you want something that will have no thermal expansion as it gets hotter and colder. Sometimes you want something that'll expand a lot.
And what about what you do now didn't exist when you were a student?
There are a number of things. I think the major development in aerospace these days is nanosats, also known as CubeSats. You can go out and buy entire subsystems that used to be multi-year custom developments, big dollars. Now you go online, you type in a credit card number, and a couple weeks later your attitude control system shows up, or your solar panels show up, and you bolt it all together. You still have to do a lot of work at the system integration level, making them all talk to each other and play nicely with each other. But you can get into space these days for $100,000 to $1 million and actually do real things, real science with these small satellites. And
so it's the materials that are different? Or the size of the materials?
It's more the packaging and the level of development. They're stock, literally off-the-shelf type things. They're not just making one of them. They're going to be making 20 or 30 of them, and they're the same each time. You can go next year and order the same part, like you're ordering something off of Amazon.
And it's a lot less expensive.
Much less expensive than the old way of doing things, which was like a full custom development. Is you'd start like, okay, what are the requirements for this specific mission? And we're going to tailor everything so that it's absolutely optimized. And it'll be a big cost plus contract where it costs what it costs, and nobody really cares about that. Here it's this is the data sheet. This is what it costs. Send us a credit card and we'll send you the part in the mail.
How do you use math in your job?
Budgeting is simple budgeting for all sorts of things, both in dollars, but also mass budgets. The entire system can only weigh this much. How does that break down into subsystems? This can only weigh so many kilograms, and so on. Power budgets. Solar panels are going to generate this much power. Who's going to, which subsystems are going to use which amounts of power, so many to the detector, so many watts to the heaters, and so on. Volume budgets, where we've got this much stuff to fit in, we've got this space to fit it in. How much does each thing take? There's also much more complicated math. It's not just a simple Excel sheet. So data analysis, sometimes you'll run an experiment on a prototype of a part. You'll have a bunch of data points. What is the data really saying? What can you conclusively prove from the data? There's quite a bit of looking at and interpreting charts.
Graphs, these kinds of
graphs, charts, data, numerically interpreting them, like curve fits and so on, but also it's just sort of visually looking at data and being able to say, yes, that squiggle is a little blip and that's not a big deal, but that squiggle over there, that's something terrifying. So for stress analysis, they can get to be much more complicated as you go higher and higher up at the instrument level, finding the resonant frequencies of various parts as they're getting shaken on the rocket. You remember there's a famous video of forget the name of the bridge, but it's at a certain frequency in the wind, it's just started shaking all over the place. It's calculating what that frequency is for satellite components and making sure they don't match up with something that your rocket's going to be driving.
What is the coolest thing you get to do in your job?
I get to send stuff into space.
That's
I get
pretty cool.
to design and build and touch things that are going to be on orbit, in space. So there's a little bit of I'm going to say a dreamy aspect to it where I mean it's the final frontier, whether you're a Trekkie or you grew up with sci-fi novels or something like that. It's the next best thing to actually being an astronaut.
So sounds like you're really excited about space, but you didn't study aerospace engineering.
So I actually looked at a number of different industries. If I wasn't doing this, I would be doing utility scale solar energy was another place that I was looking at. They both happen to be hiring. I happened to get a job here. So that it really just came down to that. There wasn't a grand plan of, I want to be an aerospace engineer and this is the ladder to climb up to get there. It was, this kind of looks cool. Yeah, these people seem like good people that I'd like to work with. They seem to be doing interesting stuff and they have interesting stuff for me to do. Let's sign on with this for a little bit. And I don't know that I'm going to be in here for the rest of my career. The aerospace industry is notoriously cyclic. When it's up, it's up. Everybody's making money, making satellites, having a great time. And when it's down, and nobody's working. So I may move on to another industry after this. In fact, I'd say to students these days that sometimes you get a job just to know that that's not what you want to do. Is go try it out, work there for a few months, and if it doesn't work out and you absolutely hate it, quit.
And that's a valuable learning lesson.
Yeah, and chalk it up to experience.
I imagine your work requires collaboration with lots of different kinds of people. Can you give us an example of some of the people that you work with?
Immediately, I work with lots of electrical engineers. There's a lot of back and forth with designing these circuit boards. From the electrical, we need more and more space. We need more room for our traces. We need more chips on the circuit board. But then you have to come back and mechanical say, I don't really have that much space. Well, what if we move this over here? And that goes back and forth on a daily basis, figuring out how to make it work, both from the electrical side and the mechanical side. I also work with quite a few non-technical people. The scheduling people, they got to know, this one's really taking a long time. What is this going to affect downstream? Or all of a sudden, we're pushing out our launch date. Maybe we need to add more resources to this problem. Accounting and budgeting. That this is what we think it's going to cost. Well, this is how much money we have. Making that work. Also with the university, procurement, travel. There's a number of people that in the system, so to speak, where you just have to make it work. Configuration management, making sure that what you do is documented and that that the part you said you were going to build is the part that's actually in the spacecraft going up on there. There's been some spectacular failures that way.
Can you tell us about a time in your education or your career where you weren't successful or maybe failed at something?
Yeah, there's a few examples. I have a tendency to want to overanalyze a problem, get a really perfect result with a really complicated equation to describe something. And what ended up happening is I wasted a lot of time and got nowhere. The numbers did not add up in the end. What I learned from that is that sometimes you have to recognize early when instead of going through a problem and solving it, you need to find a way around the problem. You need to find a way, is some way that more or less solves the greater problem that you were looking at with that doesn't maybe, attack this particular smaller individual problem.
What was your favorite experience as a student at CU?
Definitely the Formula SAE program. It was a wonderful program. You took a 600cc motorcycle engine and you built a race car around it. You went to Detroit and you raced it against 140 other schools from around the world. And it was in a number of different competitions, from performance, but also cost. What would it cost to build? How good is? And you had your design reviewed by professional automotive engineers. It was an amazing experience where you learn by doing. I mean, you raised all your own money. And you actually had to build the thing. It was engineering and practice, and that's where you really learn how to be an engineer.
What do you wish someone would have told you when you were in college?
So something actually somebody did tell me, and that I found very valuable, is that all of engineering school is really a gigantic prerequisite for becoming an engineer. And it's not even like one point where all of a sudden you stamp you on the forehead, you are now an engineer. In the legal sense, yes, you take the fundamentals of engineering, you work 7 years in practice, and then you take the professional engineering exam, and then from the state of Colorado or wherever will then stamp you an engineer, and literally you get a stamp. But in a more practical sense, it is a lifelong thing. Engineering school will teach you the fundamentals, but you have to go out there and do it, and practice engineering. Go out, build something, create something, and that's where you learn, the practice of engineering, how it actually happens. Not to say that it's some theoretical or fake thing in engineering school, but it's once you hit the real world and you start running into real world problems, a number of things crop up that you just can't teach in a lecture.
So besides engineering, what do you do for fun?
I live the Colorado outdoor lifestyle. Hiking, skiing, snowshoeing, road bicycling, mountain biking, just any sort of outdoor sports out there it's a great place to be out here. It's a great place to live. Yeah, it's just fun hanging out in the woods.
Great. Well, thank you so much for talking with us today.
You're welcome. Thank you.